Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with chapter 9 of microwave engineering, where the transmission of microwave we are dealing with for the analysis and understanding purpose with the help of a single conductor transmission line called as waveguide, and as it has the circular cross section, we have it circular waveguide. We started this chapter first of all to analyze and see the details what exactly the conventional coaxial transmission line is, and a modification by preventing the central conductor to have in the structure we have a circular waveguide having hollow cavity inside it. So as we know that the TEM transverse electromagnetic mode is not supported, we have the two alternatives, either to go with transverse electric TE mode or transverse magnetic TM mode. So in the previous videos we have gone through the solution for the equations corresponding to these modes, and we have solved selected problems on two. Let us see a problem number 2 based on to the TM mode. So here we are provided a problem statement. It is an air-filled circular waveguide having diameter of 4 centimeters is operated over frequency of 10 gigahertz in TM01 mode of microwave propagation. We are asked to determine in the part A phase constant in the waveguide, in part B cutoff wave number inside the waveguide, in the part C cutoff frequency, in the part D phase velocity in waveguide, in the part E guide wavelength, and at last wave impedance inside the waveguide. So to read the problem statement, we come to know that there it is a circular waveguide, and inside the hollow cavity of circular waveguide we have air. So corresponding to the air we can have the permittivity and permeability values, the constant ones we know here. Next to that we are provided the diameter value, the operating frequency, and the mode of propagation, that it is transverse magnetic. We have 01 to the subscript here. Now we need to determine the phase constant of the waveguide. So phase constant is denoted by beta, and inside the waveguide it should be denoted beta suffix g. So beta suffix g is equal to what is the question in part A, whereas in the part B we need to determine the cutoff wave number in the waveguide. So wave number is denoted by k, whereas cutoff we denote it k suffix c here. So kc is equal to what is the part B. The cutoff frequency can be denoted by fc here, whereas the phase velocity inside the waveguide we used to denote the phase velocity by v suffix p, but inside guide we shall be denoted v suffix small g. Guide wavelength can be denoted lambda suffix g, and the wave impedance is denoted in general by capital Z, and for inside waveguide the measurement we have Z suffix g is equal to what. So this is our problem statement. Very first of all we shall be noting down the given details. So here we mention for given details as the diameter value we have in the problem statement, it is equal to 4 centimeters. So this implies that we obtain the radius value that for the circular waveguide we have denoted while analyzing with the equations small a. So small a is equal to this value 4 centimeters divided by 2. So radius is half of the diameter, and it gives the result as 2 centimeters. As we shall be preferring the SI system of units, it will be 2 into 10 raised to power minus 2 in terms of meters here. So this is the one given value. Next to that we have been provided the operative frequency value. It is equal to 10 gigahertz here. So for giga we have the multiplicand 10 raised to the power 9. So 10 into 10 raised to power 9 hertz, or we can directly put it 10 raised to power 10 in terms of hertz for the operative frequency. We have been provided the operative mode of transverse magnetic with the subscript 01. So in general we represent Tm suffix Np here So this implies that we have small n is equal to 0, whereas small p is equal to 1 here. N is nothing but the nth order corresponding to that of the Bessel's function, whereas p is the pth root here. So for 0th order Bessel function having the first root, the corresponding root value denoted by capital X suffix np, we have to make use here. And for this combination tm suffix 01, from the tabulation that we have seen in the previous video, we have the value 2.405. So among the TM modes, it is the smallest possible value we have obtained for the root represented X suffix np here. Next to that, we have the air dielectric. So the air dielectric implies that we have the value of permittivity given by either 8.854 into 10 raised to power minus 12 farads per meter, or we can also express it in the form that it is 1 upon 36 pi into 10 raised to the power minus 9 farads per meter. Whereas for the air, we have the permeability value represented by mu suffix 0. It is equal to 4 pi into 10 raised to power minus 7 in terms of Henry per meter. So these are the various given values as per the problem statement. So we shall be making the use, and let us make the computations for part A to part F. So as per the problem statement, very first of all, in the part A, we are asked to determine the phase constant. So the phase constant inside the waveguide is denoted as beta suffix g, and we have the formulation to determine the value by taking square root over omega square mu epsilon minus, we have the ratio of x and p to that of small a, radius of the waveguide, which is to be squared in the second term here. So this is all under square root here. Now we have the value of mu, we have the value of epsilon, x suffix np also just now we have written. The value of small a radius is also determined. We don't have omega, so omega can be expressed as, being it the angular frequency, we write it as 2 pi f. So omega is squared, we square the bracket for 2 pi f, we replace mu by mu 0, epsilon by epsilon 0, and here x suffix np divided by small a, which is to be squared. So by the next step, we can substitute the values here. So inside the square root, we have the first term. So in the first term, we can mention 2 pi into f is equal to 10 gigahertz, that we can substitute 10 raised to power 10 here, the bracket is squared here. So this is in multiplication to, we have mu 0 is 4 pi into 10 raised to power minus 7, whereas epsilon 0 is 1 upon 36 pi into 10 raised to the power minus 9 here. So this is the first term here, while we have the subtraction of second term from it. So in the second term, we have x suffix np 2.405 divided by small a is equal to 2 centimeter, that it is 2 into 10 raised to power minus 2. So this is also to be squared here. So this way we have substituted all the values to obtain the phase shift constant inside the given waveguide. So by the next step, we try to get the value computed by simplification here. So therefore beta suffix g is equal to, we have square root, and the square bracket, first of all we have 4 into pi square after the squaring of 2 pi here. In multiplication to, we shall be having the 4 from the second bracket, and it will be divided by 36. So pi in the value of mu 0 and that of the epsilon 0 have got cancelled, as they were in the numerator and the corresponding denominator here. Now this is in multiplication to 10 raised to power 20 by getting the square of frequency value 10 gigahertz. So now we have from the two constants of permeability and permittivity 10 raised to the power minus 16. So this completes the first term there inside the square root, and next the value we have obtained to the 14,460.0625 here. So next to that we simplify it more. For the first term represented inside the square bracket, we obtain the value. It is 43864.9084 minus, we have the same value, 14460.0625. So after subtraction inside the square root, we are left with the value 29404.8459 here. And at last the phase constant beta suffix g is equal to 171.4784 here. So as this is the phase shift constant, the phase shift constant is always measured in terms of radians per meter. So I outline the required value that it was for part A calculations in the problem statement. So getting back to the problem statement, now we have the value of beta suffix g determined. Now next to that we want the cutoff wave number in the waveguide denoted by k suffix c here. Now for part B, we can represent k suffix c is equal to capital X suffix np, the root value of the pth root for the nth order Bessel's function, divided by the radius of the circular waveguide. So we have both the values for numerator and denominator. We can substitute 2.405 to the numerator and 2 into 10 raised to power minus 2 to that of denominator. So this ratio gives us the cutoff wave number Kc is equal to 120.25 here. So I just outline the required answer for the part B here. So after getting the answer for cutoff wave number inside the waveguide, we require the cutoff frequency denoted by Fc. Now the Fc for part C can be determined with the help of a formula that involves the terms as like capital X suffix np to the numerator divided by 2 pi a in multiplication to the square root of mu epsilon here. So while substituting the values, we can make it to the form 2.405 in the place of X suffix np. In the denominator we have 2 pi into the small value for the a is 2 centimeter, 2 into 10 raised to power minus 2. Now square root of mu into epsilon can be left with square root of mu 0 epsilon 0. So this is for the air dielectric medium, and now we know that 1 upon square root of mu 0 epsilon 0 is nothing but c here. So c is velocity of the light rays in the air or vacuum here. So the constant value for the c can be utilized here. So by the next step we go for calculation of Fc as we put 2.405 as it is in multiplication to here 1 divided by square root of mu 0 epsilon 0 to be c here. So there it is 3 into 10 raised to the power positive 8 here, whereas rest of the denominator is 2 pi into, we have 2 into 10 raised to power minus 2. So by the next step we get Fc with the form. So we get it to the simplified form that it is 2.405 into 3 into 10 raised to power 8 divided by, we have 4 pi into 10 raised to power minus 2. To the next step we have 0.57415 into 10 raised to power 10 here. So this 10 raised to power minus 2 will go to the numerator here. So here it is 10 raised to power 10, as this is the frequency, so we have to mention it in terms of hertz here. if you want to get it converted to the gigahertz, we can write here 0.57415 into 10 raised to power 9 into 10 into hertz here, and we get this multiplicand in the representation of gigahertz. So 10 into this one can be 5.7415 gigahertz as the required value of cutoff frequency FC here. So I just outline this required value for FC. So in the problem statement, out of the 6 parameters to be calculated, we are successful to calculate the 3 parameters. The next one is the phase velocity inside the waveguide. So here for part D, we denote the phase velocity inside the waveguide by small v suffix g here. So it is obtained by dividing the angular frequency omega by the phase shift constant inside the waveguide. So both the parameters need to be taken, the measurement inside the waveguide here. So omega is equal to 2 pi f we can represent, and it is divided by beta suffix g. Now whether we have all these values or not, so 2 pi is the constant, frequency of operation 10 gigahertz is provided, and beta suffix g we have just now calculated as the answer for part A. So by substituting the values, we get the form of v suffix g is equal to 2 pi into, here we have 10 into 10 raised to power 9 divided by the answer of part A is 171.4784 here. So this gives the required value of phase velocity inside the waveguide equal to 3.6641 into 10 raised to the power 8. In the SI system of units, the velocity to be measured in terms of meters per second. So for the given details, we have determined this value. So after the phase velocity, we require the guide wavelength represented by lambda suffix g to be determined. So for part E, we shall be making the use of relationship between the 3 types of the wavelengths corresponding to a circular waveguide here. So it will be having the guide wavelength, the wavelength of the microwave signal inside the waveguide, wavelength of the microwave signal inside the unbound medium, that it means it is before entering to the circular waveguide, and the cutoff wavelength inside the waveguide. So we have that one, and as we have not been provided with the values of cutoff wavelength and the operative wavelength, we can get it to the form half into the frequency and half into the wavelengths. So we get the convenient representation of lambda suffix g is equal to lambda suffix 0 divided by, we take the square root 1 minus, here we make fc by f bracket squared here. So in this representation, we can have lambda 0 obtained from the ratio c by f. So c is the constant velocity we know, f is given that it is 3 into 10 raised to power 8 divided by, we have 10 into 10 raised to power 9. So if we cancel out 10 raised to power 8 from numerator and denominator, we are left with 3 divided by 100, and finally it will give us 0.03 meters. So now we can substitute the lambda 0 value. Fc we have determined, f is given in problem statement, therefore lambda suffix g becomes, we have the numerator 0.03, it is divided by square root of, we have 1 minus 5.7415 divided by 10. The multiplicants of the giga, so 10 raised to power 9 to the numerator and denominator will be cancelling out here, so we need to get it squared here. So finally, after making this calculation, we obtained the guide wavelength lambda suffix g is equal to 0.0366. So as guide wavelength is a measurement of distance, we should measure it in the terms of meters here. So it is the length here, length of the microwave hence the name guide wavelength. So getting back to the problem statement, now we are at the last portion to be calculated here after the part of guide wavelength. So here we want the value of wave impedance inside the waveguide, that can be represented as capital Z suffix G here. So therefore in the part F we compute Z suffix G, and for this we take the help of a formulation in the terms of eta in multiplication to the square root of 1 minus fc by f, bracket is squared here. So eta is the intrinsic impedance. Generally for the air dielectric, as it is, we represent it as square root of mu 0 by epsilon 0. In general we represent square root of mu by epsilon here. So this will be in multiplication to 1 minus fc by f, bracket squared here. Now we know the values of mu 0 and epsilon 0, so therefore we take it to the form square root of 4 pi into 10 raised to the power minus 7 divided by 1 by 36 pi into 10 raised to the power minus 9 here, and here we multiply it to that of square root of 1 minus, here we have 5.7415 divided by 10 to be squared here. So we get the simplified form of the first square root to the form square root of 144 we obtain by multiplication of 36 with the 4, as it will be shifted to the numerator, and it is in multiplication to pi square, 2 pi's it will be there, and here from the ratio of 10 raised to the power minus 7 divided by 10 raised to the power minus 9, we shall be left with 100 here, or 10 square you can say, and here we have 1 minus 5.7415 divided by 10, bracket is squared here. So this simply gives to the 120 pi, that it is the ideal value for air dielectric. So we have got it calculated in a sequence here. So it is in multiplication to the second square root that results to the value 0.8187 here. So finally we obtain the value of wave impedance inside the waveguide, given circular waveguide. The value is 308.6615. As it is impedance, we should measure it in terms of ohms here. So here this completes the problem number 2 corresponding to the measurements for TM modes inside the circular waveguide with the given details here. So I hope the problem was very straightforward and simple one. By the next lecture we shall be addressing the another topic in the same chapter. The topic is titled TEM modes in the circular waveguides there. So I hope you are really enjoying learning with the microwave engineering subject. For more details and information to gain higher knowledge, you can subscribe to Ekeeda channel. Thank you.